Average value. Our objective is to use the mean value theorem for integrals and find the average value of a function. Mean value theorem for integrals. Let's start by recalling what is the mean value theorem for derivatives. Remember that this talks about that when a function is continuous and differentiable over an interval, that the derivative of the function at some value along the interval equals the average rate of change, f of b minus f of a, over b minus a. That's the mean value theorem for derivatives. So the mean value theorem for integrals, if we choose to integrate both sides of this equation, what does that look like? Well, I'm going to take this b minus a and pull this as a constant multiple out of the integral using our constant multiple property. So 1 over b minus a on the right side of the equation times the integral of f of b minus f of a. And on the left side, the integral, which remember that the integral is the inverse process of the derivative. That's the antiderivative and the derivative. So that leaves us with just f of c on this side. And then we can think of when we take the integral or the antiderivative of little f, that can be written as capital F of b minus capital F of a. Let's contain that as one expression, times 1 over b minus a, and on this side still f of c. Well, another way to think of that using our fundamental theorem of calculus is to write capital F of b minus capital F of a as the integral from a to b of the function f of x dx. We still have the constant multiple of 1 over b minus a, and on the left side of the equation, f of c. Now what we actually have right here is known as the average value. F of c, notice this right here, this is the average value of the function f of x over the interval a to b. The mean value is that c value right there. The mean value theorem for integrals says that if f is continuous on an interval a to b, there is a number c. C is an x value such that the integral of f of x dx equals f of c times the quantity b minus a. Well, how do we get that? We get that by multiplying both sides of this equation by that constant b minus a. But again, the mean value from our mean value theorem for integrals is that x value from the average value, that x value right there. So when we multiply both sides of the equation by that constant b minus a, we get f of c times b minus a. And on the other side, the integral from a to b of f of x dx. So let's talk about what this represents. Remember that the integral from a to b of f of x graphically represents the net area between the function and the x-axis. So if I'm sketching the graph of a function f of x over the interval from a to b, that represents that area like that. Now on the other side of the equation, we have f of c, which is a function value, and that's how high up the function is. So f of c, which of course we said represents the average value of f, graphically represents a height, while b minus a is the difference between b and a, that represents a width. And we are multiplying a height times a width, which gives us the area of a rectangle. Running out of room here, so let's note that up here. F of c being the height and b minus a being a width, multiply height times width, and you get area of a rectangle. Area of the perfect rectangle. If we can find one spot in here at which that we can find that height and call that at some x value c, such that this is at the y value f of c, then this rectangle that is blocked off is going to give us the exact same area as that area under the curve that originally we colored in green. So our mean value theorem for integrals is saying that we can find some point along the function at which the height times the width makes the area that is exactly the same as the area under the curve between the function and the x-axis. Again, this definite integral representing the exact area bounded by the function and the x-axis. Of course, we want to think of it as net area because if there's anything below the x-axis, that gets subtracted. So our mean value theorem for integrals says that there is some x value in our interval at which the height at that x value, the function value times the width, gives us an area of the rectangle that is exactly the same as the exact area, or the definite integral from a to b of our function. That average value is that height from that perfect rectangle. Let's look at how we can apply that with some examples. Number one, find the average value of f of x equals x squared plus 1 over the interval 1 to 3. So anytime I see find the average value, I want to think to myself that would be 1 over b minus a times the integral from a to b of f of x dx. But of course I apply it to my problem, and that's going to be 1 over 3 minus 1. That would be our integral from 1 to 3. F of x is our function, x squared plus 1, and with every integral comes a dx at the end. Now we can simplify this 1/2 and do our antiderivative, x cubed over 3 plus x, 1 to 3. Let's not forget the 1/2 that's on the outside. We plug in our 3 for 3 cubed over 3 plus 3 minus, and then plug in our 1 for 1 cubed over 3 plus 1, and we can simplify this. Inside here we have 32 thirds, so 1/2 times 32 thirds, which equals 16 thirds, or it might be easier to think of it as 5 1/3. Now why would that be? Well, let's take a look at what this exact area looks like from 1, here we have a graph of it, up to 3. Here is that exact area in here. So this 5 1/3 is the y value that gives us our perfect height. Why perfect height? Because it's the height for the perfect rectangle. So 5 1/3 is a little bit above 5, which is going to be out at that spot right there. So if I could draw that as the height of the one rectangle going from 1 to 3, notice how it looks like it has included a little bit more, but excluded a little bit more, and they look like they about match. So that would probably make sense right there. 5 1/3 is the average value of this function over the interval 1 to 3. 2. The velocity of an object is given by v of t equals sine of t. A. Find the average velocity of the object over 0 to pi. So I'm given velocity, and I need the average of the velocity. So that would be finding the average value. Anytime I think of average value, I think of 1 over b minus a times the integral from a to b of the function for which I'm finding the average value. Applying it to our problem, 0 to pi is our interval. So we do 1 over pi minus 0, integral from 0 to pi of our function sine of t dt. And then I can evaluate. This would be 1 over pi. The integral of sine of t is negative cosine of t from 0 to pi. Plug in the pi first, so keep the 1 over pi on the outside, negative cosine of pi minus negative cosine of 0. Might be easier to see it that way. And then we can simplify. That makes 1 over pi times negative of negative 1 is 1, minus minus is plus 1, or 2 over pi is our average value. Part B, find the position function p of t. Well, remember, position to velocity to acceleration. This is the order taking the derivatives, where velocity is the derivative of the position and acceleration is the double derivative of the position. So if I'm going from the velocity backwards to the position, that would be taking the antiderivative. So the position function is the antiderivative, or the integral of the velocity function. In this case, my velocity function is sine of t. So my position function is negative cosine of t plus c. There's my position function. I don't have enough information to find the exact value of c, so I can leave it like that. Next, then use p of t to find the average velocity. So now I'm taking the average velocity, but I'm doing it from the position function. So I'm going from position to velocity, which is the rate of change of the position, or the derivative of the position, over the interval 0 to pi. So if I'm starting with position and getting average velocity, that's going to be the rate of change of position, p at pi minus p at 0 over pi minus 0. Remember that the average rate of change is f of b minus f of a over b minus a, which looks very similar to what we do with average value, where this turns out to be capital F of b minus capital F of a over b minus a, because we're multiplying by 1 over b minus a. So let's see what we get when we apply this to our function. This is going to be negative cosine of pi plus c minus negative cosine of 0 plus c all over pi minus 0. Well, of course, the c's cancel out, c minus c, and we're left with negative cosine of pi, which is the negative of negative 1, plus 1 divided by pi, which is still 2 over pi. So I wanted you to see the relationship between when we have the velocity and we find the average velocity using average value, and when we start with position and then we find the average value, average velocity, where we're doing the average rate of change.